Are you ready?
Yep.
Can we get his screen on? We can. Okay.
Check.
Kevin Funk.
Seems to work. Does the microphone work? Microphone works? Yep.
Yep.
All right. Hello, welcome to QtDevCon one more last time. Today we're going to talk about speeding up your compilation using precompiled headers, CCache, and Ninja. I won't be able to compete with the presentation before regarding visuals, so we are now back to tables and command line output and C++ code. Sorry for that. But yeah, what's the most annoying thing about, one second. What's the most annoying thing about when working with C++ code? Actually, one big issue is that people and developers are really annoyed about a recompilation of your software, right? If you have the traditional legacy code base, which takes like 20 minutes to compile from scratch, each time, like some dude from the team touches the central header, you do git pull, and you see like, oh, the global header was modified. You know you can actually go out to make yourself a coffee and see that you need to spend 20 minutes again to rebuild your project, right? So this talk is a little bit helping you in that regard, that you can actually speed up compilation in these kind of scenarios, and gives you a kind of guidance how to make things faster in the usual scenarios when working with C++ code. So first of all, there is one thing to note. You could actually switch compilers to make things faster, right? There's the big fight between GCC and Clang, the friendly rivalry, as they put it. Question is, which one is better? And actually, I don't have a good answer to that, because I think it really highly depends on the project you're actually going to compile. This talk in general was adapted from one of our episodes from the KDAB TV series. Jesper, he actually ran these checks, ran the benchmarks on an internal KDAB project. There actually it made a huge difference whether you're going to use GCC or Clang. This time for this talk, I actually ran benchmarks on a public KDE project called Rucola, which is a chat client written in C++ Qt. Very new code base, very modern, very good regarding header design, like lots of forward includes and so on. And for that you can actually see, like there's a, if you look at the metrics above there, like we have a benchmark been done with running GCC under make, running Clang under make, running GCC under Ninja, running Clang under Ninja. And for that particular project, the actual compilation times, they were actually the same. So around 400 seconds for all of them. There's only minor difference. Yeah. But yeah, we had customer projects where actually switching from GCC to Clang actually made a notable difference, and we had compile time from going down from 15 minutes to 13 minutes, so quite a bit of an improvement when it comes to building from scratch. So what we're saying here is that basically, in short, you can't make general statements about which compiler is better or faster. It depends a lot on the code base, on the code complexity, and also on the optimization flags used on the compiler. So if you build for debug or build for release, the compilers differ in that regard. And even, you cannot even make sure that basically GCC and Clang always have the same speed. It also depends on which kind of GCC version and Clang version you're using, right? There are actually some nice reads about that. Their conclusion is basically Clang initially, like when it was born in, I don't know, Clang 2.x times, it was known to be faster compared to GCC, but nowadays GCC has picked up quite a bit. That's the common consensus in that regard. Because Clang was initially rather trying to be just compatible with GCC, but it has been adding optimization levels, and so on, more C++ support, C++ standard support, and so it got slower by time. There's actually this one report where it says, like, compared from Clang 3.x to Clang, I don't know, 11.x, it actually got 2 times slower. just the compilation speed, right? We're not speaking about speed of execution. This is just about compilation speed. Right, so I'm not really spending a lot more time on that because you could actually fill a whole section on which compiler is the fastest. You would actually need to spend a whole blog post on that. So what other options do we have? There is Ninja. That's my question. Who of you is using Ninja already? Maybe 20%, even less, okay. Who's heard of Ninja? A little bit more, so okay. Okay, what is Ninja? So Ninja is an alternative build system. It's a small build system initially developed by some Google developer called Evan Martin. Its focus is on speed. So the Ninja build system is really designed from a meta build system to be generated, for example, from CMake. It's not actually designed to be written by humans, like you could do with makefiles, right? Initially, like if you just have a makefile-based system, you could actually handwrite that. Ninja is not designed for that. There's just one single file which contains all the compile instructions densely defined in that file. The idea is that actually if you run the build tool, it only needs to look at that one file to figure out what kind of operations need to be done, right? And where to check whether things are up to date and whether not. Compare that to the normal recursive makefile system you're used to, right? Normally, if you use CMake and generate makefiles, you end up with a huge tree of makefiles. And as soon as you run make, actually make needs to go through all these individual makefiles, needs to parse that, needs to check whether everything in there is up to date, whether it needs to run the compiler again, and so on. And this whole recursive going through different makefiles is slow. Right. So what are the benefits of Ninja? As I said, only needs to check one single file. And especially for incremental builds, this is much faster. I'm going to show in a little demo that there's indeed a huge difference for even a moderately sized project. It actually also has a comprehensive suite of tools you can use. You can actually start it to run, so it explains to you, oh, this file updated, so I need to recompile these other files. Or you can list the dependencies of each translation unit in your project, like seeing CPP file XYZ, it depends on these headers, and as soon as one of these headers changes, it actually needs to be recompiled. It also has an output where you can see like the dependencies in a graph with graph, which is really nice. It has really compact output, and it only prints out warnings. It doesn't print out like the whole series of commands, the whole series of targets which are being built compared to make. And also really nice is that it prints the full command line execution as soon as there's an error. So as soon as something failed, one translation unit failed, you actually see the whole compiler invocation, including flags, include paths, and so on, which is really helpful. And all that on all platforms. Okay. How do you use it? In CMake, really easy. You can just pass a specific generator, which in this case is Ninja, and for this, CMake is then generating the Ninja build file system for you. It's also pretty easy to do in QtCreator. I'm going to show that as well. Building the project, you could do this as before with CMake -build. So that will run the build tool internally. The build tool used for Ninja, it's called Ninja. That's the command line you use. So let's have a look at one of our projects. I'm using one test project that's called Rucola. That's a C++ Qt code base, actually completely Qt widget based, 1,200 CPP files. That's like half of it is actual code. The other half is actually test, so it's very well unit tested. Just to give you an idea how big that project is, right? And I now have an already existing build directory in this place. It already has been compiled with make. And if I just make again, we'll see output like this, right? There's nothing to do, right? That's something which is not a nice developer experience in the end, right? If you want to hack on code, you maybe just changed one CPP file. This adds up to like the recompilation cycles. If you want to restart your application, you actually have to wait for this to finish as well every time. And yeah, it doesn't do anything in that sense. Now let's have a look when doing that with Ninja. Again, this is a build folder which has been populated already. It has already been built. Now if I just run Ninja there, that's it. And that's because Ninja just needs to look at that one file. It doesn't need to go through that tree of make files. And yeah, this is like a difference from, I don't know, 10 seconds to 0 seconds to actually do incremental builds when there was no change. Yeah. And obviously this also helps when there are just little changes, right? Because you always get these 10 seconds of make having to run through all the things. Yeah, I hope that motivated you to use Ninja. Just a quick hint how to do it in Qt Creator. You can do it. You can set Ninja as the generator in your kit. If you go to Options, then go to one of your kits, like this. At the bottom, there is the CMake generator you can choose. And actually, here you can use a different generator. Yep. That's all you need to do. OK, what other options do we have, right? So we fixed the build tool already. Now, maybe we can do something about making actual compilation a little bit faster. And there is CCache to the rescue for that. What is CCache? CCache is a compiler cache. It means that it caches previous compilations of translation units. It detects when the same compilation is being done again, and it reuses the build artifacts in that case. Okay? It's available for GCC Clang, very well tested for GCC and Clang. Just recently, it also gained support for MSVC, which has traditionally been rather not been well supported in that regard. As far as I know, the maintainer, he just restricted himself from merging that support because it was just too complicated to code base. Right? But at some point, they gave in, and MSV support is in CCache. Actually also done by the Qt company. I think Christian Adam, thanks to that, worked on that. Yeah. OK. Let's see how it's going to be used. So there are two ways to use CCache. You can actually prefix your compilation commands with the CCache command. So instead of just running GCC, you do CCache GCC. Alternatively, you can just masquerade CCache as your compiler. How is that done? So if you install CCache, you actually end up with a folder which contains a set of symlinks. In that case, we see symlinks for C++, CC, Clang, G++, and so on. And these symlinks all point back to the CCache library. And right. So the idea is, when you run G++, you want to basically get pointed to that symlink, and instead of running G++ proper, you actually run CCache. And CCache takes care of invoking G++ again. Okay, so that's the trick. You actually export path to add this path which contains the symlink to your path. So G++ actually goes through CCache all the time. These are the two ways. Much easier under CMake these days, at least this is a super old feature actually. You can run CMake with -CMake C compiler launcher equals CCache, and then CMake will take care of actually prefixing every command you have there with CCache, and it will always go through that. Okay. How do we check whether CCache is working? We start a fresh build of our project. We run CCache -s repeatedly. -s gives you an output of like how many hits did we have in the cache, how many times did we actually have been able to pull out one of the artifacts from the cache. And then we touch some file in our project or switch to some old branch, try to build again, and now the build should actually be almost instant, right? Because when we touch files in a project, we actually need to recompile source files, but just touching means we just change white space. That means we can actually reuse the same exact build artifact as before, because we have done this compilation as before again. And then, in the end, we actually run CCache -s again to check whether we actually had hits in the cache. So let me demo that for a second. Right. So I'm currently in a Git-based project. And now what I want to do is, I'm currently on master branch, and I just want to check out a super old branch in that project, okay? I now did that. Now let me try to rerun Ninja. Yeah, ignore these warnings. Actually, we can see that it's starting to rebuild the complete project, right? Because we checked out an old version. That means like all the CPP files, all the header files are probably have been touched, have been changed at this point. It's an older version of it. Okay, we'll stop that because it will start compiling the branch. Now let's switch back to master again. Now, what would happen is, like, we changed back to master. Again, all the source files have been touched, updated, modified time, right? So if we rerun the build tool again, it will actually redo all the compilation, right? Everything has been touched. But now let's rerun Ninja. Again, we can see from the number below there that actually 2,670 targets need to be recompiled, right? But at this point, I already did that compilation. If you look at the speed here, it's actually super, super fast, right? It's actually compiling CPP files, or trying to compile CPP files. But as we've done this compilation before, it actually figures out this CPP file has been compiled like this already. So it pulls out all the things from the cache. Actually, it shouldn't do that. This is too slow. You can actually see from the speed that these files are not being picked up from the cache right now for some reason. Maybe I touched too many things. But actually, this should be almost instant. Okay? I'm not sure why that is happening now. That's bad. But with CCache, you can actually see what's happening. There's this hits section with direct and preprocessed that actually gives an idea how many files are being pulled from the cache. I'll run it again. And unfortunately, for some reason, it doesn't work right now. You can see that actually the misses counter is being increased, right? This 8,974, line 5. If I rerun that again, it's actually not hitting the cache. I'm not sure why that's happening right now.
Try git clean.
Sorry?
Run a git clean so that you at least will recompile those 800.
Yeah. But yeah, doesn't, let's forget about that, but usually, like, if you do these branch changes, like go back, CCache will kick in, because you did the exact same compilation before, with the same compiler flags, with the exact same source code. CCache will put that in the cache and will pull it out again. One thing to note is that CCache has some overhead when it misses the cache. The CCache author typically says that typically the overhead when there's just cache misses, it's typically in the range of 5 to 20%. So yeah, compilation speed will decrease by that amount. So if the expected hit rate is low, there might be a net performance loss when using CCache. So if you start, for instance, my example for that is I sometimes have to recompile Qt, right? For recompiling just Qt, and when not working on Qt, I do not want to use CCache, because that will just add overhead, and it will also add files to the cache I'm probably never going to use, because I'm not switching branches in Qt. I'm not actively working on that project, so I don't need this cache there. So you can actually temporarily disable CCache when doing this compilation there. And for that, you do CCache _ disable equals 1, and then the build tool, and then basically CCache is being disabled for this run. Right. CCache has a few more command line options which are helpful. You can run CCache -h to figure out most of them. Actually, CCache has a limited cache size which you need to control using these arguments. Let's jump over to precompiled headers very quickly. So what are precompiled headers? There's another way to speed up builds by actually using compiler features. In general, what are precompiled headers? It's a standalone header, including others, which is actually being compiled into an intermediate form. Actually, the next time the compiler sees that, it actually doesn't need to do that whole parsing of the header to use the header when compiling CPP files. It's a lot faster to process for the compiler to see it in the intermediate form instead of having to reparse all that. It's a super old feature. It's I don't know, it's like a 20-year-old feature, but only recently CMake actually has gained support for enabling that. Before it has been really, really difficult. You had to resort to using custom CMake scripts. But also, again, the Qt company did spend some work on that. Christian Adam, again, thanks to him, he actually worked on getting proper PCH, precompiled header support in CMake. So what problem do they solve? Reduce compilation time. Header files contain large amounts of source code. One example is just including QWidget and then running that through the preprocessor. It actually leads to a source file containing about 100,000 lines of code, 29,700 in my case. So that's quite a lot, right? And if you have, like the Rucola project, have 1,200 source files, or like most of them including QWidget, every time one of these translation units needs to be compiled, the compiler also needs to parse that QWidget file. That's obviously bad, because it's redoing this job all the time. Especially bad if this header isn't QWidget, but some obscure boost library. Especially bad in that case, because template-heavy code is even worse to parse, takes more time, more stress on the compiler. All major compiler vendors support it. Microsoft, GCC, Clang, they have been supporting that for like forever. I'm again taking that Rucola project as an example. In that table, you can see that when compiling Rucola without precompiled header, it actually takes us 390 seconds to compile. If we use PCH, so precompiled header, and that in that precompiled header, there's just the Qt core include, then it actually goes down to 304 seconds already. So that's a 25% speed up. In that example, we also did some other tries, like including more than just Qt core in that header, like Qt core, Qt GUI, Qt core, Qt GUI, and Qt widgets. And in the end, the author of Rucola, he also started like handcrafting this precompiled headers. Like inside this project, he actually checked which headers are being used the most often, and then he started adding like exactly these headers inside the precompiled header. So these are being cached. And with that, we get the result of 297 seconds. But if you look at like the last 4 rows, there's not a huge difference, right? So this, in that case, it appears like just precompiling the Qt core header actually has the most benefit, right? That's what we take from there. And basically, that's also what we recommend when working with precompiled headers, is that basically you try to check yourself which kind of headers should go in there, and you actually do some profiling based on that. We also wrote a little script. Jesper started that in the KDAB TV series. I fixed up your Python code. I'm going to put it in the KD toolbox. And with that script, we can actually do a couple of tricks, like figuring out in your project which kind of includes are included the most often, and also run mutations based on that. Like as you see here, first include Qt core, then do the whole build of your project, take the timing, then include Qt core, Qt GUI, then take again the timing, and so on. And it will there also helper scripts, which are going to help you like figuring out which kind of includes should be put in there. Give me 3 more minutes, please. I was in a rush. Rucola, that's actually the set of headers it's including. So basically QObject, QTest, QJSON document, so a lot of the Qt core area, despite QVBox layout. But yeah, actually, we've seen including Qt core has the most benefit. Let's quickly go through how CMake does this, or how you can actually do this in CMake. First of all, CMake 3.16 is required. Only precompiled headers are only supported since that. That's the synopsis of the command. There's target underscore precompile underscore header. Then you choose a target, and then you say which headers it's going to be used, which headers it should use in that for that target. And you can actually say, like the usual target underscore commands, that this should be public dependency or private dependency. That means if you use the target, then the precompiled header is going to be, if you do public here, then actually anything depending on the target, it will also pick up that precompiled headers. So you can actually pass that through your project. How is it used in practice? It's like this. For Rucola core, you could actually say that for anything for Rucola core itself and anything using Rucola core, it should include Qt core. Qt core, that's the header which includes all of Qt core, like Q core application, QString, and so on and so on. And privately, because some CPP file uses Boost, you could use that. Boost is just used internally, not exposed to the outside. Then you would use private and use the Boost inside one of the precompiled headers. Rucola common, for that, or that's an alternative way. If you want to handcraft your precompiled header, you would do it like this. Rucola underscore common underscore PCH.h. That one you would handcraft and write includes there. How is it used in practice? That's like the common pattern we use for adding precompiled header supports to our projects. We define an option which toggles enablement of precompiled headers. Then define a function, a custom function for that project. And that one checks the option internally, and only if that option is checked, then target precompiled headers is used. And we actually pass on all the arguments to that custom function to target precompiled header. And it looks like this in practice. Okay? So we can skip that. That's about implementation detail. There's also the possibility to reuse artifacts. If you ever created a precompiled header, you can actually reuse. Normally, CMake would use a separate generated precompiled header for each time you do target precompiled headers. This one basically saves you from that. But you need to take care to use the same options, flags, definitions for both target and the other target. You can disable precompiled header support on individual files. Very important if you have like a large set of unit tests, which are tiny, which do not need to take advantage of precompiled headers. There you can disable them. Okay. Drawbacks, very quickly, Jesper. I got a very few time, right? When changing headers, part of a PCH a lot, you shouldn't use them in the PCH, because anytime that PCH changes, anything depending on it will have to be recompiled. Not every header can be precompiled. Define, for instance, if you depend on defines before including stuff, that cannot work. Actually, anything which goes into PCH is going to ignore all the defines which have been previously set. There's an additional maintenance burden. you actually, if you use precompiled headers, then anytime you include that inside your CPP file, then all the headers inside the PCH, they are included in your translation unit, right? That means the includes inside your CPP file, they might get out of sync at some point, right? You include, for instance, QApplication in your CPP file. You could even remove that include for QApplication because the PCH brings it in. Source code would still compile, but it would actually break if you disable PCH support in your project. So for that reason, we usually recommend to do a specific CI build which has PCH disabled to check that everything still works even without having PCH enabled in your project. Okay. CCache needs extra enablements to be able to take advantage of PCH, of precompiled headers. For that, you actually need to set the sloppiness to a certain level. You need to set these two options, PCH defines and time request, so actually CCache will not be confused by precompiled headers. The implementation detail, you can look it up on the CCache configuration, on the CMake documentation page. Not going to discuss that now. Putting it all together, when should you use precompiled headers? On projects with large translation units. So we usually have that problem that we have legacy code bases with tons of code, tons of includes inside headers, which we cannot change, we cannot fix them. So there, precompiled headers make a lot of sense because we can make the compilation speed faster just by injecting those, especially with template-heavy code. But we always say profile first. CCache for projects you actively work on, like where you switch branches a lot, there it can really, really help and make your workflow much smoother. Ninja, we can basically recommend it for every platform out there. At KDevelop, we actually actively use that on the CI for all platforms, and it works fine. Leads to quicker incrementables for developers. Perfect tool to be able to leverage that, yeah. That's it from my side.
Over time when your boss is sitting down there waiting to get the stage.
I'm sorry.
Anyway, is that the people from upstairs that's down here now? They're coming in. Excellent. Good. So, as I said, let me just tribute to Kevin. A large part of the groundwork for the 2 episodes that I put out in Qt Widgets and more on this stuff was in cooperation with Kevin, a lot of talking forth and back. He had a few details. My episode is a year old now, so there's a few more things there, but I went into some more details on other things and have some plots and some graphs and discussing a bit more in details on especially the what parts should you include in your precompiled headers. Anyway, all right. I found this random man at the street and said, hey, dude, how about the closing session? Are you up for that? And well, should we start by giving Kevin a final hand here?